This is now a summary of our insight into a theory, practice, pragmatics of modeling. Our main statement will be models and modeling forms the fourth dimension of computer science. Of course, we should maybe first think why we model so often. There are a number of reasons why we do it. Often the complexity of origins is far away from what we can handle. There are hidden aspects. What we would like to have is a quick and fast understanding. We would like to have a good interpretation, of course within our biases and deep models, based on the data we have on hand, and for instance on data that we never can capture. We are humans, and for this reason we have maybe a completely different style of thinking. Modeling is based on separation of concern and eases somehow digestion of whatever we have. We want to concentrate on, focus, maybe only for a certain purpose, consider the model. And of course modeling is pretty convenient, and we avoid information overflow and maybe also something like forbidden areas. That means in this case we have now a large area why we want to model. And for this reason I go now with this a little bit larger agenda to an explanation. Models are everywhere in life, science and engineering. And for this reason we should have some kind of common treatment. Another thing is the claim that modeling is essentially the fourth dimension in computer science, and especially in applied computer science. And for this reason we should really explore it properly and integrate it in our developments in computer science. If we talk about models, we should also talk about the structure, the architecture, the configuration or the composition of models, and in this case we need to have some kind of approach to that. Our claim is that models are instruments, and for this reason we should now consider which artifact, which sort might become a model, what is the model being of an instrument, and of course we should consider the resulting anatomy of a model. That means in this case we need maybe to handle it in a proper form. I propose that we use the classical first order predicate logics approach to define a signature of a model. A signature of a model allows us maybe to inherit a certain mold, a certain way how to define things in a proper way, integrated somehow in the tools, and then to concentrate only what is maybe the normal model. Of course we need foundations. Foundations means in this case we should be able somehow to support model work and especially model-based reasoning. And of course we would like to show that this is really useful for computer science. And I claim that next generation programming is modeling to program, or models as a program. And in this case we might show that this way is really possible. One statement: this talk is the extended version with longer explanations. We have a German version, same slides, but much shorter explanations in the YouTube video that is accessible via the given link. Okay, let's start. I claim models are used everywhere, anytime, by everybody, for everybody, at any sphere of human activities, in any context. We are surrounded by models. And in this case, maybe we should consider what that means. What are our spheres? What are the aspects we consider with models? Okay, let's handle first the aspects. The aspects here are: models are used for representation of our thoughts, of our insights into things, and maybe of the artifacts we would like to represent. We call these artifacts later origins. Or models are used as some kind of guiding instrument for realization. Or models are used to understand what we do, to formalize, to make sense. In this case, we consider the foundations and intelligible aspect. In computer science, we neglect it quite often, but models are also used in daily life for interaction in our society, for socializing, for expressing our emotions, for collaboration, for orientation. They are an essential part of our social being. That means in this case we have now 4 different aspects that could be covered maybe by one model, but I think one model will be a little bit too complex. For this reason it is better to have a number of models that are well associated. We call those well associated models model suite. If we concentrate, as we do in computer science, on model usage for description and prescription, that means for system construction, then we consider only the representation aspect and the realization and context aspect. The rest is somehow neglected and not so much important. That means in this case we have, of course, a chance to use a model to express our thoughts, our ideas, our understanding, and somehow to use a model for construction of a system. In this case, a model is again an instrument that is used for this system construction, that is essentially a system construction scenario. Okay, if it is so important, then maybe we should integrate it pretty well into our computer science or our applied computer science. So far, computer science is a very broad area with a lot of subdisciplines. And the situation is somehow similar to the situation mathematicians had in the 50s last century. Mathematics became almost unteachable. Then a group of French mathematicians, the Bourbaki group, tried to develop a structural point of view for mathematics, and this structure-oriented mathematics resulted in 3 main guiding dimensions for mathematics. Maybe we should do the same for computer science? We claim that modeling is the 4th main dimension of computer science. We might add additionally approximation and human-computer interaction as other dimensions, but we could consider the 4 main dimensions. That would mean in computer science we typically apply computer science to express our understanding on the state or the structure. We have states in the large, or structures in the large, and in the small. In the small we consider types and schemata as we do it in databases. In the large we do it especially for software engineering based on architectures. The second dimension that is quite often considered as a first main dimension in computer science is transformation. Transformation we have in 2 different somehow directions. One is evolution of changes, integration, migration, consolidation, that is nothing else as transformation in the large, and transformation as change of states, maybe by rules, by computation or methods or anything else, but is somehow considered as transformation in the small. The same third dimension can be also separated by collaboration expressed through communication, through coordination, through cooperation. That is nothing else as collaboration in the small, and for this reason we can somehow express in the 3C framework what means collaboration. Collaboration in the large could be also collaboration of systems based on exchange architectures and services. And my claim here in this talk, and I think in general it is a true claim, the fourth dimension are models. Again, models based on what we do with the models, idealizing, distorting, extending, amplifying, or how we develop models and our understanding about our systems in computer science. That is based on abstraction, comparison, mapping, construction, reflection, organization. Most people consider abstraction as a main interesting part. I would say all 6 somehow activities are main activities for models. Now we have 4 dimensions. Are they different for different branches in computer science? The answer is yes. Consider, for instance, database and information systems. For database and information systems, we mainly consider, of course, the state. In a smaller, let's say, part, we are interested in transformations. Our system should support us properly, so we don't have to consider so much about transformations, and we can base the transformation on query languages. Collaboration is, let's say, some issue, but not the main issue. The main issue besides the state is modeling and models. In all different aspects, we have here models as maybe one of the main parts beside the state consideration. If you consider theoretical computer science, we are mainly interested in transformations. That is the same state what we have also in programming. Models don't play so much. States are of interest only when the program and the transformation should be somehow refined. Collaboration is not yet so important. In communication systems, it is different. Collaboration, especially communication, is the most important part. States and transformations and models are not as important. If you go to software engineering, of course, we are interested in somehow program development, architecture development, and system development, and for this reason, transformations are the most important part. And of course, also state in the large. A little bit on collaboration, a little bit on models you can observe. That means in this case, we can now refine our understanding of different subdisciplines in computer science based on the 4 different dimensions. You can do it in a form that you say, okay, fine, what is of the main interest? Consider, for instance, my lovely information systems area. In this case, we are interested in states, and this is our main interest. We are also interested in models, and we are also interested in transformations, at least on the basis of our query languages. Additionally, we are interested in data that are digestible by humans. For this reason, we consider also the 5th dimension, approximation, is not of importance so much. If you go to theoretical computer science, of course, the main issue is transformation. Collaboration is not really important, but it will become important very soon. Modeling is not as important, but it will become more important very soon. States are somehow considered, but not really properly considered. If you go to technical computer science, then you have a similar picture. Collaboration is very important. Transformation is the most important part. Modeling, okay, fine, it could be important. If you go for the coding part, for the basic data types, then in this case, modeling is not important at all. Approximation is not important at all. And human-computer interface, oh my god, forget it. If you go to algorithmics, then you have a different picture. Again, transformation is the most important part. Data structures, okay, fine, they support somehow, but are not really important. Modeling should become very soon very important. The same picture you can observe for programming. You can also look for business informatics or applied computer science. In this case, modeling is a central part. States are considered really properly. Transformations are hopefully somehow given in some way. And of course, the human-computer interface is of interest. You see that the 6th dimension, approximation, is not yet really very well considered in our disciplines and dimensions. I think this will become more important in the next future. Often we claim modeling is not important at all, and for this reason we have a number of myths, a number of misunderstandings that are in our area quite often stated. I have here 20 different statements. I could also somehow summarize 40, 60, 80 different resistance myths. One could be each hype must have its modeling language. That is common practice nowadays. But maybe we should inherit what we have been learning in the past. Another thing is models can be discarded after being used. A third thing is modeling can be practiced as handicrafts or in art by everybody whenever it is necessary, and it can be forgotten whenever models are not the central part. We have also somehow model-based reasoning is based on deductive systems, or there is no commonly accepted or acceptable notion of a model. That means we have a number of myths, and if you look through these myths, then you will see, oh my goodness, something is really maybe somehow important to be reconsidered. And I will now show that this is possible. Let us now step towards a general theory of models. If you go to computer science books and to our lecture books or course books, then you will find a lot of different notions of models. I claim here 1001. Maybe we should ask ourselves, is there a general notion? Or maybe that is a little bit too heavy a question. Maybe we should ask, is there a generic notion that can be refined towards our specific area or specific sub-discipline we are considering? What is essential of a model? I think we should now try first to get some insight into the structure of a model. You could call it architecture, I would call it configuration of a model. And this can be based on our model house. Of course, the model is in the center of our consideration. Of course, we use models within some kind of applications scenario where we have tasks, where we want to have a result of the application of the model. In this case, the application scenario and the sphere defines the profile of the model. What is the goal? What is the purpose? What is the function of a model in this scenario? This is now somehow on the surface. In reality, however, we are inheriting whatever has been done before. First of all, we start with a general mold, with a general methodology that can be successfully applied in our area. That means in this case, we have something like a general guideline that is commonly accepted. Furthermore, our models contain an intrinsic part. You could call it somehow deep model. That is accepted in our subdiscipline, and for this reason we should use it in a proper form, and we should forget to talk about it, since it is obvious. Both parts form the matrix of our model. Furthermore, modeling is supported, for instance by concept spaces for conceptual modeling, or by knowledge, or by theories, or by observations. It is also enabled somehow, especially by languages or other tools, tools for reasoning, tools for representation, for reflection. And we have some kind of acceptance of a model by a community of practice. And of course we embed the whole thing into a context. A model reflects origins. These origins are not the full, let's say, collection or set of origins we could consider. These are the most essential ones, the most important ones. And of course they come with some kind of restrictions. Let's call them invariants. A model should, of course, respect these invariants, and the solution we target should also somehow respect these invariants. That means the origins are reflected in the model, and the origins allow us to draw some results. The result must not be an artifact. It can be also thoughts. That means in this case the model science is far more general than only the creation, the making of some artifacts. This is now, of course, a pretty large configuration of a model. In reality, we consider only the model, the origins, and the results we would like to consider, and the application scenario drives us to do this modeling in a certain specific way. We forget about the matrix. We hope that the supporting means are somehow sufficient. The enabling means are also sufficient for the work, and of course we live in our community of practice, in our context, for our application scenario with models. And models mainly are instruments for solving a task and delivering a good solution. That means in this case we have now a pretty large configuration of a model. If we consider, however, what is here in light blue, what is maybe in yellow, then we have a far less difficult task. And for this reason, maybe we should consider modeling as somehow given by some kind of matrix, given by some kind of means, and maybe also embed the context somehow, and only consider the rest of this model house as a configuration of a model. Can this be really properly done? Yes. Look, for instance, for conceptual modeling. In this case, we have a very specific configuration. The matrix is given, the community of practice is given, the context is given, and of course we have a very specific application scenario, namely the construction of a system. In this case, we consider for our model, we would like to develop whatever is given as a support, ontologies, dictionaries, our knowledge, whatever we have here. And of course we have enablers, mainly languages that allow us to express our thoughts in a certain way. And then we model, and this is nothing else, if we look a little bit more properly to it, as a triptych. A triptych that says what are the supporting, what are the enabling means, and then please model your banking example, your banking data structure based on the knowledge you have already got. If you close this triptych, it becomes a diptych. The diptych, of course, forgets about anything what is supporting and enabling. It is mainly somehow whatever we can digest or reason, and whatever can be expressed somehow. That means in this case we target on the diptych and would like to develop a triptych of conceptual models. That means our model house becomes in this case far simpler, since we assume that the configuration is pretty specific, and for this reason we can consider this specific consideration in a proper way. Okay, maybe we can now come to a general model science. The model science is a pretty old issue. We should start with Heraclitus and his logos, review whatever people have been doing in the past, Stachowiak, also review whatever has been done for computer science. I would name especially Bernd Marr. And we should now ask ourselves, is there a general notion of a model? A general, maybe generic notion of a model that can be refined whenever we know a little bit more about our application area. And we can ask ourselves first, what makes something to become a model? What is the model being of something? That means it should be somehow clarified what it means. Let's go back to classics. Herbert Stachowiak has, in one of his reviewing papers, given three model characteristics. There is an origin, or an original he called it, that it models. The model is an abstraction with respect to the original or the origin. The model has a purpose with respect to the origin. That is a general characterization, but it is not really convincing and not really refinable. Maybe we should use a little trick. And the trick goes back to Hermagoras of Temnos. He had a rhetoric frame, and the rhetoric frame is based on answering 6 questions. Who, what, when, where, why as the main questions. In what way? You could add by what means. And this could characterize the model being of something in a more proper way. And in this case, maybe we can have a general theory of models, generalizing whatever has been done in the past. In this case, we might develop an anatomy of the model being. If we go back to our model house, then we have, of course, to clarify what are the origins, what is represented. Of course, we would like to use a model, and for this reason we have a concern in an application scenario and a usage, so the model becomes an instrument. And within this application scenario, the model has to function. That means we have a purpose, a function, and a goal. The purpose is somehow supported by means, it is extending the goal notion, and the function is embedding the whole thing into the application scenario. Then in this case, of course, you have maybe some kind of restricted concern. Then in this case, you have an application domain and a context. Furthermore, you focus. Focus is nothing else as our horses are focused by some clubs so that they can concentrate on the street and not being irritated by anything else what is driving around. The focus really allows us to reduce our attention to the most essential, relevant and typical parts of our origins. The next is what is implicitly assumed or inherited. In this case, we have the deep model and the mold behind. How we are supported, how we are enabled. And of course, a model should be somehow representable, and I claim it is mostly represented by a number of models in a model suite, and these models in the model suite are well associated and their association is maintainable. So that means in this case, we have now 9 parts of the anatomy of the model being. So there's nothing else as a structure of the model being. So we can answer now which instrument, which artifact, which sort can become really a model if we consider these anatomical parts of the model being. If we want to consider it for the special configuration we have already considered, then the matrix is given, the community of practice is given, the context is given, and the specific application scenario is also given. In this case, our origins are less general. The purpose, function, and goal are mainly based on what we want really to achieve, to understand, to plan, to design, sometimes to explain, to explore, to predict, and to use. The application domain and the context is far more restricted, but the model becomes now harder and better usable, and the focus, of course, is restricted, and the assumed and inherited assumptions are somehow injected. And if you go to this paper I'm putting here with the reference, then you see how this is done for conceptual modeling. Okay, that means in this case we have now something like a general approach to modeling. Not yet, we do not have yet a notion of a model, but I think we should come to some kind of notion of a model. Okay, the notion of a model combines different things. First of all, the model is an instrument that functions in applications. And in this case, we can concentrate on two main general properties, on adequacy and dependability. Adequacy is well accepted everywhere. Dependability is the thing that is somehow hidden in the matrix, but we should make it explicit in order to reason why the model is even functioning, why the model is appropriate. In this case, we come now to a notion of a model. A model is, of course, an instrument. Let's say we would like to have nice models. For this reason, let's say we have well-formed instruments. We consider origins, a collection of origins. These are adequate. We generalize the mapping property to analogy. We generalize truncation or abstraction properties to focusing. And it is, of course, purposeful. I think what is widely neglected in the consideration of models, but taken into consideration anyway, is dependability. We should believe in a model. We should find the model really appropriate. And in this case, we should have a justification. And, of course, the model should be of a certain quality. That means we are able to reason on the quality and to evaluate the quality. And we are able to justify why we are using this model in our application scenario, why it functions. In this case, we have a corroboration. The model should be coherent and conform. The model should be somehow falsifiable or verifiable. The model should be stable and plastic. That means in this case, we have something like a general model theory that says a model is nothing else as an instrument. Well-formed, of course, are considered only that is adequate and dependable. Of course, a model has also a background that comes mainly with our deep, or with a model inside, or with a matrix. We have a grounding and we have a basis. And the model being is driven by directives, the functions, the origins to be represented, the context, and the community of model believers. In this case, the model has also somehow an inside part. And we can now use this general notion of a model as a generic notion and specialize it in the same way as we did already for our conceptual model with a very specific configuration, forgetting about what we have to say about the deep model and the mold. That means forgetting the matrix, but assuming that everybody accepts the matrix as well. Model should function. Model should also be effective in our, let's say, I would say, usage game according to Wittgenstein's language games. How I can now specify a model? I propose a pretty simple approach that is very successfully used in classical mathematical logics, the onion approach. You define first a set of terms and then a set of formulas to be somehow part of this language, and you start typically with a signature. The signature is nothing else as the vocabulary you are using and the restriction of the meaning of the vocabulary. That means we start with some kind of stereotype. We can use the same approach for the definition, description, usage of a model. Begin with the model stereotype. Use some model definitions, use a modeling style, use some origin packages we would like to get directly and inject into our model, use some foundations, and have some kind of enabler, tools and technologies, and then you describe the model. If you look a little bit more on this picture, you find this picture looks like the classical LaTeX onion approach. You accept whatever is given by the model class or by the class. You accept the definitions, you write or rewrite or reuse at least some styles, some packages, some foundations, and you have some tools somehow for the generation of the result of your text. That is the same. Can we do the same for our area? The answer is yes. Go for a specific signature. Go again for conceptual modeling, for instance, with a given matrix, with a community of practice that loves the approach. Let's say the entity relationship modeling approach. And in this case, you have a context and a specific application scenario, and you are oriented on a database system construction. That means we do nothing else as defining a general data structure, and this is now the class that defines directly our data structure. And now we use, of course, object relational platforms, and in this case we orient our definitions already on that. We go for the modeling style, use some kind of global as design approach. That means views are local derivable views, maybe as complex schemata as well, but anyway, they are derivable. You use maybe the insight you got into financing and booking, and you have some kind of theory behind, you have a tool behind, and then you state only your normal model and the view models, and you say, okay, fine, now I have been describing at least the structure of a database application. That means in this case, you hope that the tool will now generate the result. The result would be in this case a physical database schema. It has been shown that this is achievable and possible to do. Of course, in this case, you need a lot of theory behind. You should also somehow know what means model-based reasoning. And of course, you should use the modeling instrument, in a pretty skilled way. And of course, we will have later something like a culture of models and modeling. Okay, the theory is now, of course, the heavy part. We claimed already that anything can be a model. It depends on the community of practice, on the application scenario, on the enabling and supporting means, on the matrix we are considering. That means whatever can be incorporated, anything can become a model, at least for a certain while. Maybe not in general, maybe only for a certain purpose, but anyway, we are using this anything for something. Models could also be specifications, but typically we are not targeting so much on formal stuff. Model-based reasoning is now the really heavy part, and we realize that model-based reasoning is completely, or at least essentially, different from the classical deductive calculi. Since a model is an instrument, we mainly orient on the utility, on the usefulness and the usage of a model. And these are now the main criteria for the model being of something. The invariants are transported. Bernd Marr has been stating that there is nothing else as a cargo. The invariants are transporting from origins to the result the main properties that should somehow be integrated into our application game. That means a model is nothing else as a model of and a model for, and both parts are valid. In many research papers you find the statement that only one of them is important. I think that is a misunderstanding of the for function. For means also maybe some kind of mental change. And we can use the rhetoric frame in order to provide at least some kind of survey of the model. We call this survey informative model. You can extend the rhetoric frame to the so-called W*H framework that has a bit more refined questions that should be answered for a model. Models should not be complete. due to the scope, the focus, the application scenario, the function we consider, and for this reason we have a problem. That is a problem of deductive systems. Deductive systems should have the complete knowledge of the background. We don't want to have the complete knowledge. That means in this case we should go beyond deduction. And of course in this case we consider also model suites, and model suites of course should have also a proper maintenance, tracers, and in this case we should have maybe some kind of model association framework that the model suite is really properly representing what we want to have to be functioning in an application framework. That means in this case model-based reasoning goes beyond deductive reasoning. Reinberger was calling this kind of reasoning frameworks subduction. I think that's a nice notion. Subduction includes, of course, induction and abduction. Induction concentrating on something, based, for instance, on the Occam-Brazos principles, or let's say on the principles by Solomonoff or Kolmogorov. I would call them modesty principles. And they are used somehow whatever on the material, whatever we have. That means they are often used in evidential reasoning. That is the first step only. The next step is plausible reasoning. That means it should be somehow acceptable what we do with the model. And in this case we have to consider a lot of different forms of reasoning mechanisms. Of course abduction, of course induction, but also analogy, autoepistemic, counterfactual, default, and anything else of reasoning techniques we have been learning with the first waves of artificial intelligence research. Additionally, a model allows us to focus on something that in this case is somehow valid. That means in this case we consider approximative reasoning. Approximative reasoning integrates, of course, what kind of aggregations we are using on our data. Some, let's say, things are not really observable. We observe only somehow shadows, how Platon was somehow stating. For this reason we should have some kind of approximative reasoning that allows to reason on aggregations, on generatives, that is partially imprecise, at least so imprecise that we can tolerate. And in this case we have maybe completely different reasoning techniques. Those techniques are available, but they are outside the classical first order predicate logics reasoning. We should also go for second order, third order, fifth order predicate reasoning, but we should also go for other kind of reasoning mechanisms that are appropriate for models in certain areas. And of course dependability uses now different reasoning techniques for justification and also for sufficiency analysis. Justification can be done maybe logically. Sufficiency analysis is often done numerically, or at least based on a property framework. Okay, is it really worth to have such a large set of methods? We claim that the current usage of models for programming can be easily extended to modeling to program, what is essentially already done by model-based development, model-based analysis, and other approaches. We can extend it to modeling as programming, and in the future we might dream of using a model as a program or instead of a program, because of the model already contains the whole program, the rest can be generated. Is it achievable? We claim yes. We have had 2 workshops already on modeling to program. The second workshop has been published here in this Springer CCIS proceedings, and we have the first workshop. The dream was at that time that we go away from models for programming, where we use a model as an inspiration and a blueprint for programming, towards modeling to program in a systematic way, beyond what is done so far in model-based development, towards modeling as programming, towards models as a program. That means this is some kind of ladder of maturity. Is it possible? We claim yes. We have 3 showcases where it was already somehow shown. One is LaTeX, another one is the classical compiler-compiler approach, or maybe also the ASM, the abstract state machine program generation. We have been doing 3 case studies. One, of course, for databases, another one for mapping or somehow generating the BPMN model out of the storyboard, and we have been using the same also for website engineering. That means in this case, the model usage for models that allow us new generation programming is, of course, an achievable goal. Okay, let me summarize somehow. We go, I think, in the next future to a general modeling science. Modeling will become a sub-discipline in computer science and also in applied computer science, and will be done systematically. What we have so far, we have parts and pieces for a general foundation of modeling. We can use a trick, stereotype the model function, and in this case you have models for representation, models for domain situation, models for prescription, models for description, models for perception, conceptual models, usage models, explanation models, investigation models or sort models, and you can have also meta models, something like guidance models or steering models that allow you to have a proper workflow for the application game you are somehow using. And of course you should have better reasoning schemata, and you should have a proof of concept. I think the proof of concept we have so far is sufficiently good to be very optimistic that this program is really somehow realistic. If you want to have more information, please go to my YouTube channel or to Academia Edu or to ResearchGate, where I have been putting my own thoughts about models since 2009. 2020 and 2021 will come soon. This will now be the end of this lecture. I thank you. Any claims, critics, suggestions, or let's say even collaborations in our model clubs should be sent to Bernhard Thalheim at email-uni-kiel.de. Models are far more general than we consider in computer science. Let's say you have something like these data schemata, or you have some general models, or you have some BPMN diagrams. You can have also some kind of general means. You can go to medicine. You can go, let's say, also to some kind of evolution of systems, or you can go, let's say, to astrophysics. All this has been already captured in a volume we have been developing on modeling and to model in the past. One of the nicest model I know is this clock of Antikythera, built in the wrong world model, in the Ptolemaic worldview, being as precise as clocks could be, even far more precise. You can here see the place where the Jupiter is, or the Mars is, what kind of sun problems you might have. All this could be seen on that clock. That means in this case you have a very sophisticated model of the world based on a specific matrix, but it is almost correct for whatever we have, and it is almost precise. It is even more precise than our mechanical clocks we have so far nowadays. That means in this case you have models everywhere. That is now the picture for science. You can make the same picture for engineering. You can make the same picture for life. That means in this case we are living in the world of models in order to live in the real world in sciences and in engineering. Thanks a lot.